Hi everyone, this is Jessie speaking. Welcome to our KDD tutorial, Learning with More Data. So this is a joint work between Penn State, University of Minnesota, and Shanghai Jiaotong University. So I will go ahead and get started, and then the rest of the part will be shared by the other speakers. I'll start with the motivation. Everybody says we live in the big data era these days, and a very representative dataset is ImageNet, which has more than 14 million labeled images. So everybody knows this dataset. However, when we are dealing with our real tasks, maybe we are facing the challenge of the small data that we only have a small amount of data. Take image classification, for example. Say, even though we have more than 14 million images on ImageNet, maybe the task we care about is to classify these two types of dog, which they look very much alike, Boston Terrier and French Bulldog. I bet for the audience who never saw any of this kind of dogs before, maybe it's very hard to tell the image I show here whether it's a Boston Terrier or French Bulldog, because I'm only showing you 6 labeled images. And that is actually a Boston Terrier with the question mark over there. So this is an example of few data samples which make the learning task very difficult. Another example is when we are training robot to do stuff like human, we may want to only show the robots a few samples. Say, for example, place this ball in the from the bowl to the plate, and whether the robot can actually learn from that very few data samples of behavior, so the robot can repeat. That's another small data example. And something that also relate to my research is we do a lot of research on mining spatial temporal data, in particularly city data. And we find nowadays many big cities have started open city initiatives where they put city data publicly online. For example, New York City put a lot of data online. They have a New York City open data portal. If you search for, say, taxi data, New York has a very good taxi data set, and they keep updating it. So does Chicago. You can see a lot of taxi trip data that is public online. However, when you search for taxi data on Boston website, you don't find any such kind of data set. So this is another example that if you want to predict the taxi demand in Boston, and that's going to be very difficult because you don't have a lot of historical data set. So what if you only have small training data and you still want to use such data for your machine learning tasks? And typically there are two ways to get help. On one side, you can get help from auxiliary tasks, which are the tasks that may be similar to your target tasks. And you can also get help from domain knowledge. So our tutorial will mostly focus on these two categories. On one side is how to transfer knowledge from auxiliary tasks. And another big category is how to use domain knowledge to boost the performance of machine learning model when we face small data. I'll get started with the first category, how to transfer knowledge from auxiliary tasks. And so just give an overview. The idea of this big category is that we have some source tasks, and from those source tasks we can train a model, and then we transfer the knowledge. Basically, we transfer what we learned from the source task data to the target tasks, and we train a new model for these target tasks. And here we present 3 types of learning techniques for this, how to make use of the auxiliary tasks. First is the transfer learning. In the transfer learning, the setting is that we only have one source task, and we also only have one target task. And for the multitask learning, we have n source tasks, and we have the same n target tasks. And for the meta learning, the setting is we have n source tasks, and we have another n plus 1 target tasks. So they actually deal with different kind of settings. So we will talk about representative technique for each of the category. We'll start with the transfer learning. So for transfer learning, as we just said, there's only one task and another target task. And so a big category under transfer learning are supervised transfer learning and unsupervised transfer learning. So the difference between them is whether the target domain has a few label data or has no label data at all. And usually in the transfer learning, we assume the source domain has enough or sufficient label data to learn a reliable model. But for target domain, we don't have too much. So we'll talk about the first one is how to do supervised transfer learning. And this category maybe most people are quite familiar with. So in the supervised transfer learning, so let's say we have the same task, and this task is to classify whether this image is a Boston Terrier dog or a French Bulldog. And since we only have 6 labeled images, that's definitely not enough for us to learn a reliable model to differentiate these 2 kinds of dog. So typically nowadays, the state of art is actually we'll use the ImageNet, in particular for image classification. We'll use the ImageNet to learn a source model, and we use this source model as our base model, and then further fine-tune based on the images we have for our target task. So typically people use neural nets or deep learning. So the idea is for the source task, this is the neural nets we learned with multiple layers. And for the target task, we make the lower layers share the same kind of, we make those layers share the same kind of parameter. We call those tied layers. And then the upper layers we call adaptation layers, and those layers are trained or say fine-tuned on this target label data. And the reason we are doing this is usually the lower layers will capture the fundamental semantic understanding of the images. For example, if we're doing face recognition, the lower layers probably will detect some of the meaningful sub-images that tell this is a human's eye or nose or eyebrow, those kind of stuff. And then the higher layer are more towards classifying certain kind of people's face. So the similar idea is here. So the lower layers may capture the dog's nose, eyes, and ears, etc. So another type is unsupervised transfer learning, where the target domain has no label data at all. And the idea, since the target domain, we don't have any label data. So the idea is actually we try to make the target data, the feature space, has a mapping that's similar to the source data feature space. And in the implementation, we usually add a term that's the loss on the distance between between the source data samples and the target data samples in the feature space. So to give an example, mostly frequently used distance is the MMD. So is the maximum mean discrepancy. As you can see here, say this is a source domain, and this is the target domain, and this is the two-dimensional feature space. So we are learn a mapping that map them to this new feature space. And in this feature space, we hope that the distance between the source and the target data are small. So basically, we try to minimize their distance. And the way to define this MMD, as you can see in this formula, so XS are the data samples in the source domain and XT are the data samples in the target domain. If you define them as MMD, and that's defined as basically you take all the data samples in the source domain and take the mean of those data samples. And you can think about this is like a representative data samples of all the data samples in the source domain. And similarly, you take the means of all the data samples in the target domain, and this, of course, this is after the mapping. Okay, after the mapping, you take the mean of those data samples, and then you want. So basically, you see the difference between the representative mean data samples in the mapped space between the source data and the target data, and you take the L2 norm of that. So you try to make in the new mapped space the source data and the target data to look similar. This is most frequently used measure, MMD, and in particular is used in this ICML paper. So basically, as we just said, so we have some tied layers, shared the lower layers, and in the adaptation layer, so we try to make the source and the target to be similar in the feature space, in the mapped feature space, by measuring the MMD distance between them. And a more recent work, that's ICCV 2019 paper, they changed the MMD to a new distance measure. They call it MMFND, and this is the basic maximal mean feature norm discrepancy. And you can see they look very similar, okay? But the difference is, so first they will take the L2 norm of the mapped data. So F and G basically are the mapping of the data. So G are the lower layers, and then F are the tied layers. So basically you map those data first, and then you take the L2 norm of that data. And then after that, you sum, or first sum over all the norm of all the mapped data samples in the source domain, and you take mean over that. And then minus, well, you sum over all the norms of the mapped target data samples and take the mean of that. So basically, you first calculate the norm first and then see the difference. So that's different from the previous one where you calculate the distance first and then take the norm. But this method surprisingly works very well. And for more details, you can look at this paper shown here. Of course, another way to make the data in the target domain and the source domain to be similar is using the idea of adversarial method. So basically, you have a mapping and you have a discriminator, and this discriminator try to differentiate whether a data sample is from the source domain or the target domain. So you basically want the source domain and the target domain to be similar after the mapping. Okay, so that's the big idea of this unsupervised transfer learning. You're basically mapping the data samples from the source domain, target domain to be similar. And that's all about transfer learning. So we move on to the multitask learning. As you can see from this figure again, so the multitask learning, different from transfer learning, usually has n tasks, and the target has the same n tasks. Okay, and in terms of method, there are three type of method called hard parameter sharing, soft parameter sharing, and task routing. So actually, the method is quite straightforward. Let's say you have three tasks, task A, B, and C. And the hard parameter sharing is basically make the lower layers to share the same kind of layers in the neural nets. And the soft parameter sharing is to allow the difference between those bottom layers, but having certain constraint to make them look similar. Okay. Uh, so those are two very straightforward methods, and more recently, there is a method that's kind of taking the advantage to make it more soft. So the idea of this method is called layer routing. Uh, so this idea is actually some of the layers they are shared as colored in orange, and some of the layers are probably task specific, like the pink for this task and the yellow for this task. Okay, and maybe some of the layers are even skipped. Okay, so different from the hard sharing or soft sharing. So this framework is more flexible. And in terms of the implementation, the loss function has three terms, and this is our typical term of the loss function to be similar with the labels. And this is a sparsity, basically to add all the weight together to make the weight to be sparse. So most interesting is the last term in the loss function is the sharing. So basically we want the weight. So basically we want encourage them to share the same layers, especially for the lower layers. We would encourage them to share the weight more. As you can see, the lower the layer is, the smaller the lowercase l will be, and the weight will be larger. And then we want the weight on those layers to be similar. And this is straightforward because usually in the neural nets, the lower layers are the fundamental building blocks of the images, and the higher the layer is, the more task specific it is, and we allow them to be more, specific towards the target tasks. So that was the idea of this paper, and that is about the multitask learning. So for the next part for meta learning, Huaxiu will take over and talk about it.